Hello, and welcome to another ME372 lecture. I would like to start today's lecture by talking about one of my heroes. And this picture here is of one of my heroes, Dr. Librescu. And Dr. Librescu was born in Romania during World War II. And he had a really rough life as a young kid. It was really challenging for him to get an education. But with diligence and hard work, he obtained a PhD and became a professor. And he was a professor at Virginia Tech, where I received my PhD. And I actually had a class from Dr. Librescu, and he was just amazing. Here is a page of one of his notes from his note packet. So this is just a typical page. Everything was handwritten. This is page 25, and you can see that in the development of these equations, we're on equation number 58. Here's 60 and 61. And we were supposed to read through these notes and somehow understand this material. But the way in which Dr. Librescu taught, it was such that you did learn the material. And it was one of my favorite classes that I ever took as a student, even given these difficult pages to try and understand. It was an advanced class in stress analysis of plates and shells. In 2007, there was a gunman that went to Virginia Tech, and he went into the engineering building. He chained the doors shut and then went around to classrooms and started shooting people. Dr. Librescu was teaching a class at the time. He was actually teaching the very class that I had from him, and in the very classroom that I had it from him. And when the gunshots started getting closer, Dr. Librescu ran to the door and slammed the door and held the door shut while his students were jumping out of the second-story window to the ground. The gunman tried to break into the room, and in doing so, as Dr. Librescu was holding the door shut, he was shot to death by the gunman. There's no doubt in my mind that that single act has landed Dr. Librescu to the exact place that I want to end up someday. I have the highest respect for Dr. Librescu. I love the man. I love what he stood for, and I love how he lived his life and what he did at the end of his life. I would strongly encourage you to read through this little history that was published about Dr. Librescu. And I would encourage you to try to be a Dr. Librescu. Try to be like him, follow his ideals, and learn from his examples. He's one of my great heroes, and I will never forget what he did for me as a student in the many times I was in his office for office hours, and how he taught me the mechanics of materials and stress analysis, and then what he did at the end of his life to try and protect his students with his life. Before we get into combined loadings, we need to define what we call a stress element, because we will use stress elements throughout the rest of the semester. And so it's important that you understand what we mean by the term stress element. So stress elements are a convenient way to visualize the stresses at a point in a body. A stress element is drawn with finite dimensions, but represents an infinitesimal point at a specific location. In general, stress elements are three-dimensional, and are drawn as 3D cubes. However, in many machine design applications, and in most of those that we use in this class, because of the loading in geometry, the 3D stress state is reduced to a 2D stress state, and a 2D square can be used to illustrate the stresses. So for us, most of our stress elements will be in 2 dimensions. When using 2D stress elements, the stress element typically references a point on the surface of the machine component. Since the stress element represents an infinitesimal point on the structure, the stresses must be equal in magnitude and opposite in direction on opposing faces. So tension stress is illustrated by arrows pointing away from the element, and compression stress is represented with arrows pointing into the element. And shear stress is shown to act along the sides of the element. The figure below illustrates 3 stress states or 3 stress elements on a cantilever beam. Element A represents the infinitesimal point at the top center of the beam, indicated by the shaded region. So even though this element A is shown as a finite-sized element, it represents a single point, a single dot, right at the very top of the cantilever beam. Element B here, shown as a finite-sized element, represents the point exactly at the 90 degrees angle from element A, right at the end of the beam. And element C here is just at some arbitrary location on the surface of the cantilever beam. So the important thing to remember is that stress elements in 2D represent an infinitesimal point, and we draw them with a finite size. In practice, stress elements are placed at locations of maximum stress. These locations are typically found using shear moment diagrams and experimental testing. When a cut is made in the member, the stress elements are placed so that one edge of the stress element is right at the cut. This edge is referred to as the cut edge and is used to determine the directions of the stresses that act on the stress element. So assuming a cut at the wall in the cantilever beam shown below, the cut edge of the elements A and B would be as shown in red in the figure below. So here's a top view of my cantilever beam on the previous page. Looking straight down on the beam, we would see element A, and the cut edge of element A would be shown by this red line. The cut edge for element B would be going right into the page. Here we're looking at a side view of the cantilever beam, and we see the cut edge of element B. So it's important when you draw a stress element to always represent what we call the cut edge. And the cut edge is where you make the cut in the machine member.